So I'll go over some of the ROM sets that can be run from the PacMan emulator. So the first ROM set is just a standard PacMan. So when it starts up, it just goes through like memory tests, which is with all the funny characters on the display, and it goes into the attract mode. So this is like just the standard attract mode. It just goes through this, and you can see this one is Midway manufacturer and branded. If I start up the game, and as you can see, it's like the standard PacMan maze, and on standard PacMan there's only one maze, and you just play it, and it gets harder as you go up the levels, and as you grab the ghosts, the eyes go back to the center, and you get the cherries and stuff for the special bonuses. But there are other ROMs that will actually run on this emulator once you've emulated the PacMan PCB. So the next one I'll go to is Miss PacMan. So Miss PacMan will also run under the same PCB emulator. And the track mode is different, so it goes through a different set of animations for doing the Miss PacMan emulation. And as you can see, it says Miss PacMan up here, and on one of the ROM sets that's slightly different, which I'll just discuss. I'll let the track mode just finish its animations first, then Miss PacMan comes on. And then if I start a game, as you can see, it's a different maze to the PacMan maze, and actually as you go through Miss PacMan there are a number of different mazes for each level. There isn't a maze for every level, but it starts repeating the same mazes again after you go through about 4 levels or something, I think. And the cherries come on from the side, as you can see there, rather than go from the top. But there's another ROM set, which is a Miss PacMan ROM set. Oops. A Miss Pac Attack. So when this one starts up, the actual track screen is the same as the Miss PacMan one. So actually, if you came up to the track screen, you wouldn't know whether you're playing Miss PacMan or Miss Pac Attack. But when you start a game, you can see the maze is different on Miss Pac Attack, and the first maze is particularly challenging because it has these like stepped bits in the maze, and it has a number of different mazes. And in fact, actually, one of the dip switches that you've got when you actually do an emulation, so I think I've made it dip switch 9. What will actually happen when you switch that dip switch on, if I just reset it and start a game. Now, rather than actually start, what will happen is it will make out like it's actually finished the maze, and it will go on to the next maze. And this actually helped me making sure all the colours were correct and everything, because you can just let it go through all of the levels, and when it gets to the top level, it comes up with the standard PacMan bug that you've seen on the display, but you can get to see all the mazes and everything, and you can just make sure the emulation for the colour schemes and everything is correct by switching on that particular dip switch. And then if you switch the dip switch off again during a game, you can actually play the level that you got up to, and they're a lot quicker on this level than they were on the previous level. So next ROM, so this top one is Midway branded PacMan. So we've seen Miss Pac Attack and Miss PacMan. Then there's a Namco branded PacMan. I won't show these because they're just got Namco rather than Midway written on it. And then there's PacGal, which is the same as Miss PacMan, but rather than saying Miss PacMan on the actual display, it says PacGal for some reason. I'm not sure what PacMod is. It's just a different set, and I think it may play slightly different, but not really noticeable. And then the only other one apart from the actual original one which I started with is PacMan Plus. So if I go into that, and when you actually start a game of this, it's slightly different. So the attract screen is the same, so I'll start game, and as you can see down in the bottom right hand corner, the actual level graphic is slightly different, but the actual gameplay, I think gameplay is probably slightly different, but not really noticeable as being different. But the ghosts turn into pumpkins, and like I say, the actual thing, rather than the cherry, it's a Coke can on that particular thing. And as you go through the levels, you get so if I just switch on dip switch 9 again to go through the levels, as you can see, then there's a like cocktail icon rather than, I think, is it a peach or so? Oh no, a strawberry would be the standard second one, but rather than a strawberry, it has the cocktail, and then it goes on to a pea pod, and it goes through other ones as well. So I'll go over the way that the sprites work on the PacMan PCB. So in RAM, there's an area of RAM for sprites, and it's not very large, but each of the sprites is represented by 4 bytes. So one of the bytes is the ID of the sprite, then the color reference in the color table for the sprite, the X position in pixels of the sprite on the display, and the Y position of the in pixels of the sprite on the display. So the ID itself, most of the bits in there represent whereabouts to look up in the sprite ROM for the actual data for the pixels of the actual sprite itself. Now I've placed the sprite ROM here on the arcade PCB. The sprite ROM wouldn't be part of CPU memory. I've just placed it here because it's nice and convenient, and if I want to run this on a microcontroller, then it means I don't have to have lots of RAM. I can just reference it here. So the actual these memory locations for this tile ROM and the sprite ROM, they're not actually used in the actual PacMan PCB itself, so I can just place them there. So all but 2 bits of this ID represent where the actual graphics are within the sprite ROM, but the 2 lowest bits represent whether or not the sprite is horizontally flipped or vertically flipped. So if it's horizontally flipped, you've got your 4 tiles for a particular sprite arranged like this, and each tile is a set of 8 bytes, actually 16 bytes for PacMan. On other systems actually it would be 8 bytes, but for PacMan you're talking about 16 bytes, because well, each byte represents 2 pixels represent each color reference. So you've got 1 byte representing 4 pixels, and each of the color references, because there's 2 pixels, it's 4 colors it can represent. So the actual sprites themselves can have 4 colors in them. So if I take a ghost as an example, so one of the colors on all the sprites has to be a background color, which is transparent. So the color 0 is always the transparent background, but then you've got 3 other colors. So the ghost color itself would be 1 color, the pupil of the eye is another color, and the actual eye itself is the 3rd color. So that's 4 colors in total for the ghost. So that's why you need 2 bytes to represent each row of the sprite, of one section of the sprite. And if it's horizontally flipped, first of all you need to reverse the horizontal bytes so that they go the other way around. But you can see here it makes the graphic look like this. It doesn't look right. So you also, as well as reversing these bytes around, you have to reverse the pixels within the bytes as well, which then turns the character around the opposite direction. That way in the sprite ROM, all they need to do is have one orientation of the graphic for pointing left, and it can also point right as well, just with a bit being set in this ID byte of the sprite. And the same for vertical, so there'll be a PacMan which is vertically downward pointing, and then in order to make it upward pointing, they'll have the vertical flip bit set in the ID, and it will then point upwards as well. So the color reference in the actual sprite ID or the sprite bytes is I think it's 4 pixels, and so that gives you 2, 4, 8, 16, and then these 2 extra pixels here give you 64 colors. So in the game you can select from a palette of 64 colors, and each sprite can have 4 of those colors within it. So the configuration file for this particular emulation on my emulator, the display is vertical orientation of display, and it's 288 by 224 pixels. And here's the color table. So 64 colors in total, 64 sets of colors in total. So each sprite or tile has to be a background color first of all, because they're ordered like this across the screen. So the Ghost 1 eyes has one color, Ghost 1 dot in the eye has another color, and the actual Ghost 1 has another color. So they're kind of ordered like this, and then you just go through and you fill out what all of the actual colours are. So like the colours for the strawberry. So there's memory mapped I/O, and there's I/O for enabling the interrupts on the actual system itself, CPU interrupts, and enabling the audio or disabling the audio. There's a register for flipping the display. That's not the actual sprites that I discussed before. It's actually to flip the whole screen. So if it's like a tabletop rather than an upright cabinet, tabletops, because you've got players sitting on each side, this actual register here will tell you whether or not the player 1 or player 2 is playing. So for player 2 you need to flip the display around, and then there's outputs for LEDs, coin lockout and coin count. And I don't use those in my emulation because they're not there, because they're physical devices, and I don't really have physical devices on my emulator at the minute. And then there's stuff for the audio, which I haven't set up yet, and output of sprite RAM, horizontal and vertical flip as well, which are on different ones, and a watchdog timer as well. There's a hardware watchdog timer, so if something happens and the hardware watchdog timer times out, but the software hasn't reset it, then the actual whole machine will reset. There are 3 input ports for player controls and things like coin inputs for credits. So these are player 2 controls, service switch, player 1 start, player 2 start, and then there's an input for dip switches. So that's addressed 5080. And these are just my emulation representations of key presses, so I can map the key presses to the actual emulated I/O ports, which I'll go through in my source code. So this is the source code for the actual emulator of the PacMan PCB, and it just does sets up like the display, which is just a pixel mapped display in Linux. Initializes the Z80 CPU for emulation. There's a bit of mirrored memory. So on PacMan, the high score and credit is taken from mirrored memory of the display memory. So it only writes the high score and credit to that. So if you're emulating and you don't have high score and credit text on the display, but you have all the other PacMan game and everything else, then it's because you haven't mirrored the memory from 4000 to C000. So this high score and credit is written to C000, whereas the rest of the game is written to 4000. So all you have to do is mirror the memory on top of each other, and you get the high score then placed upon the actual upon the rest of the game as well. The actual high score value is written to 4000. It's just the text. It was kind of weird, and I couldn't work out what was going on at first. Then I set up callbacks for the Z80 for the clock. So for every clock pulse on the actual Z80, I get a callback. Then I get a callback for when the system is reset. I get a callback for whenever memory is accessed, so I can do memory mapped I/O. And there's one Z80 port which is on the PacMan PCB, which is port 0, which is in use. Then it goes in and starts emulating the actual system itself, and when that's finished it terminates and closes down the display. So when the reset happens and the Z80 calls back this routine to say, okay, the CPU's reset, now you need to reset your hardware, it loads up whatever ROM set has been selected from the actual emulation menu. And I've got 2 color schemes. So the color scheme you saw was just like the standard PacMan color scheme. In my emulator there was like an alternative one which I've set up, which I quite like the color scheme. It's just something I could do because I'm emulating it. It's not important really. So this is a memory map callback, so any memory mapped I/O, so if port input 0, I can map up key presses to actually key presses on my keyboard to actually key presses within the game itself. So whenever someone presses a key to credit the actual game itself tells the CPU, okay, the key for crediting the game has been pressed. And that's the same for things like the player controls as well. If someone has pressed the left key on the keyboard, then it will say, okay, the input on this is set, so like the left input has been activated on the actual arcade machine itself. And then there's another set of inputs which are acting in exactly the same way, and then there's dip switch inputs as well, which are on a separate input, so that's where all the dip switch stuff comes from. And then there's a port which is the actual where the game tells the hardware watchdog counter to reset, so the game periodically resets the watchdog counter so it doesn't time out and it doesn't get a reset. But if the game crashes for any reason, then this port doesn't get called and the hardware will reset and the game will continue to work. And this is the only Z80 port on the actual PCB which is actually running. And this is for setting the interrupt vector for one of the Z80 interrupts. Now the actual PCBs themselves, I got the system up and running by using this method, which is using interrupt mode 2, where the Z80 itself provides the upper 8 bits of the interrupt vector, and then the actual hardware provides the low 8 bits of the interrupt vector, and that points to an address where the actual interrupt address is to actually be called. So that's interrupt mode 2. But I was finding that other ROMs weren't working, they were just hanging as soon as they get to the memory test. That's because some of the PCBs, although they have all the same hardware, so they could support interrupt mode 2, some of the actual ROM sets use interrupt mode 1, which is equal to RST38, which is a much simpler way of doing interrupts. So you need to support both of them, and you'll find in this clock callback here, so this is for every clock pulse, I make a decision as to whether I'm in interrupt mode 1, in which case I do this call to interrupt to the interrupt address at 0038, so in the lower part of memory, or if I'm in interrupt mode 2, then it provides the interrupt vector for the interrupt to actually call the correct address. So this is every frame period of the actual display, so 50 Hz on what I'm emulating. It checks to see if the hardware watchdog counter is timed out, and if it has, then it provides it activates a reset pin on the CPU and resets the machine. And then I do key lookups on my keyboard and place any key presses into these variables so they can be used in the hardware memory mapped I/O that we went through previously in this part of the video. And then I handle if I go into the user actually editing the dip switch settings. So when I brought up the dip switch settings on the display when you saw me in the emulator at the start of the video, this is the bit of code which actually does that. It actually displays what the current dip switch settings are and allows you to actually edit it, and it keeps going around this loop until you press a key to come out of the loop, and then the dip switches have been changed. And the only other thing in the actual emulator is to actually redraw stuff on the display. Now there's a weird thing about PacMan in that the display itself is the actual game plays in the middle of the display, but there's two lines at the top and the bottom of the display which are placed on the side of the memory map, and if you just display them like you would the whole memory map, the actual game plays in the middle, and then you get the high scores on the left, and you have the bottom where it shows the lives that you've got on the right, whereas they should be at the top and the bottom of the screen. And I think they've just laid that out that way so that it's convenient for them mathematically, because then they get like a 256 by 256 pixel array, and I think that's more convenient for them to do that. So what you have to do is first of all display the two bars at the top and the bottom of the display, and take the data from the sides of the display to do that, which is what this does. And then you display the display frame, which is the central bit of the display where all the game is, here. And then you display the sprites, and you display them after the actual tiles which have just been displayed up here. So this is displaying the tiles of the actual game, and then the sprites get displayed next because they get displayed over the top of the actual tiles. And also you display them in a particular order. So I've displayed them in the forward order here, I think. Yeah, yeah, in the forward order, so that the PacMan gets displayed over the ghosts. And if you find the ghosts getting displayed over the PacMan, then just reverse the order of the way that the sprites are displayed. And it just does a display refresh. And this is where I have interrupt 38. I need to remove the interrupt request after it's actually been serviced.